So, hello everyone, I am SRIPAN. I'm working as a PMRF at IIT BHU and conducting these sessions once in a week. And uh, this is finally the last week for this particular course of fluid dynamics for astrophysics, where we'll discuss about the resistive MHD scales. That means your magnetic diffusion is higher than your magnetic advection. So, one of the basic consequence of resistive MHD is magnetic reconnection. So we'll have some MCQ questions and some observational evidence of magnetic reconnection and how we can prove magnetic reconnection while we are doing some research work. So I will try to discuss briefly all of these aspects of reconnection scenario, or in more general the resistive MHD scales. So let us start with our first question. So here are four statements, we need to choose the correct one. So first one is the magnetic reconnection is usually associated with plasma heating. Magnetic field topology is unchanged by magnetic reconnection. Magnetic reconnection does not have any relation with plasma heating. Then magnetic reconnection is associated with changes in the magnetic topology. So before understanding or before try to find out what are the correct statements, we need to find out what is magnetic reconnection and when it can happen, right? So if we recall our magnetic induction equation, which is del B del T equals to curl of B cross B plus eta grad square B, right? So this is your magnetic induction equation. Now first one on right hand side is the magnetic advection term, which is related to the magnetic flux conservation or Alvin's flux freezing theorem. Second one is the magnetic diffusion term. That means you have eta, which is magnetic diffusivity, and grad square B is the second order gradient of the magnetic field itself. So as you can see from the second term will be dominating if the eta is very much higher in a localized region, and it can happen that if your grad square B is very much higher, that means your magnetic field has very steeper gradient. Now one of the scenario for steeper gradient can be like you have totally anti-parallel field lines which are very close to each other. So here you see after over a very small length scale you have very high change in the magnetic field, right? This is let's say if this is B, this will be minus B. So you have 2B change over a, let's say, very small length scale delta L. So this will give you this is, let's say, delta L. So this will give you very high del square B here. That means your magnetic diffusion will be very much high. So now what are the implications of magnetic connection is let's say if you have this positive or negative fields, so what will happen that if there can be a region between these field lines which is known as current sheet. So why we are taking like current and a concept of current sheet is if there are two field lines which are antiparallel to each other, it is possible only if there is a current source in between that. So what we expect is there should be a sheet with high current density in between these two oppositely directed field lines. Okay, now when magnetic reconnection happens, so first of all you have magnetic energy which is stored in your magnetic field lines, right? Now you have some storage of energy, and when this reconnection happens, that means your reconnection can change the topology of magnetic fields, that means how they are connected to their food points. So let's say this is your first scenario. So what can happen is they can come close to each other and then let's say reconnect here, right? So if they reconnect here, so what will happen, so you will have this kind of a fill line, right? So this is like this way, and fine, and this one may like this way. Okay, so this is a magnetic connection scenario. Now the implications are the stored magnetic energy can be transformed, or can be transformed to heating energy due to the ohmic dissipation. Now how do ohmic dissipation occurs is you have a J, which is your current density, so J square over sigma, that will give you the ohmic dissipation, which will give us the plasma heating. Now as this J depends upon the total current over the unit area. Now what happens is, since we are closing two magnetic field lines to each other, which are merging with each other, the area over which the current sheet is there will increase, will decrease, and which leads to the maximization of your current density, and that leads to the maximization of this term. Therefore the plasma heating will be dominant there. Also there are another process which is apart from heating, the magnetic energy can be changed to kinetic energy of charged particles present in that localized region, such that the accelerated charged particles gets accelerated. Okay. Now as you can see, during magnetic condition what happens, now this field line will have some foot points like here or here, and that should have foot points like here and here. Now what happens is, this is A is connected to A prime, and here let's say this is B is connected to B prime, right? You can extend it like this one, right? Let's say you have some closed loops, so you have this kind of a field line. Now A and A prime, B and B prime. So what happens when you have this? So you have A, you have B, right? And then you have A prime and you have B prime. Okay. So now you see the foot points of, or the connectivity of the field lines are changed from the initial connectivities. So this is the change of magnetic field topology. So keeping all this discussion in mind, if we try to find out the correct answers, so we'll find out the magnetic connection is usually associated with plasma heating due to the ohmic dissipation, and ohmic dissipation becomes dominant due to the presence of high current density in that region. Also, magnetic reconnection is associated with changes in the magnetic topology. So these two are correct answer for this particular question. Okay, so let's do second here. So okay, now the second one question is, so second question is like, during magnetic reconnection, now magnetic flux is not conserved, magnetic flux is conserved. There will be a finite electric field at the X point, and the width of current sheet is proportional to the inflow speed. Now so magnetic flux is not conserved basically, since this is a resistive process. So magnetic flux remains conserved only if we consider the advection process and your diffusion term is not dominant. But here your diffusion term is dominant in the magnetic connection, and one line statement of magnetic reconnection is diffusion is important for magnetic reconnection, but it does not mean that if there is diffusion there should be reconnection. It can happen, there is diffusion, but still there is no magnetic reconnection. So Nevertheless, in magnetic reconnection, your magnetic flux will not be conserved. So first one is correct. Just a second. Okay, so your first one is correct. Then magnetic flux is not conserved, obviously. So there will be a finite electric field at the X point. So when we are talking about MHD scales, what we tell that, okay, if everything is in non-relativistic regime, we assume that electric field is a secondary quantity depending upon the E plus B cross B equals to E dash A, right? So when we are writing the ideal MHD, what we find out that you have E plus B cross B, right? In ideal MHD, you have this equals to 0, right? So that means if you have an observer who is moving with the fluid, then you can think that, okay, there is no change in the electric field, or there is no electric field which can be felt by that observer who's moving with the fluid itself, right? But when you are considering the resistive MHD, then instead of this 0, what you have is you have eta, and then you have a J, which is the current density and magnetic diffusivity, right? Now this E plus B cross B is basically the total contribution for the electric field at that particular region, and now this is a non-zero value, so there will be a finite electric field at the X point. Okay, okay, so the next question here is choose the correct statement. So in the Sweet-Parker reconnection model, the outflow speed far from the X point is independent of the magnetic Reynolds number. In the Sweet-Parker reconnection model, the outflow speed is independent of the density of the plasma. In phase-check reconnection model, the outflow speed can exceed the local slow magnetosonic speed near the X point. Finite resistivity effects assume importance. So obviously the last one is obviously correct. Now we need to understand what are the correct options among A, B and C, if there exist any other correct statement. So let me give some seconds. So what is the difference between Sweet-Parker and phase-check reconnection model is, so in Sweet-Parker reconnection model, we assume the total current sheet will have a larger length, right? So it will cover the entire length over which you have the difference in the magnetic field. So but what happens is, since your diffusion time scale in that case will be much higher, so it cannot explain those impulsive scenarios like the solar flares, because those are happening at very smaller time scales, and this Sweet-Parker reconnection model cannot explain that due to the longer time scale of diffusion. So now and in phase-check model, what happens is the current sheet's length will remain smaller, that means it is more localized, and that leads to smaller diffusion time scale, which is comparable to your solar flare. But here what happens is there is some presence of MHD shocks in the phase-check reconnection model, which basically accelerates the process of reconnection, right? So Okay, now what happens is, so in Sweetberger model, what happens, the outflow speed is essentially the Alpine speed. Okay, so is it independent of magnetic Reynolds number? So obviously your Alpine speed depends upon your magnetic fields and density, right? Not on the magnetic Reynolds number. If you remember the magnetic Reynolds number, it depends upon the velocity, length scale and magnetic diffusivity, and the outflow speed does not have any dependence on these parameters of magnetic Reynolds number. Instead, it depends upon the Alpine speed. So first one is correct because it does not depend upon the magnetic Reynolds number. Second one is the Sweetberger reconnection model. The outflow speed is independent of the density of plasma. Now, as you know, that outflow speed is depending upon the Alpine speed, and Alpine speed depends upon the density of the plasma. So, it is depending upon the density of the plasma, right? So, this is not a correct answer. Now, the in phase check reconnection model, the outflow speed can exceed the local slow magnetosonic speed. Yeah, it's true, because in a phase shift reconnection model, what happens is it is more faster than the Sweetberger reconnection model, and so therefore the outflow speed will be higher than that in the Sweetberger reconnection model, right? So in Sweetberger reconnection model, your outflow speed is equal to your Alpine speed, so we can assume the for obvious reasons the outflow speed in the phase shift reconnection model can exceed the local slow magnetosonic speed, which is very much correct. So So let us move to this question here. So the question is okay, now see here, this is a GIF, and okay, let us start from beginning again. So we will explain, we'll try to explain it. So what you have is, this one is J3, so you have this one is XY plane, and you have a J3, that means your magnetic field is defined in your X and Y, okay, and J3 is giving you the current density. So as you can see that in the entire region, the current density is in between this 0 and very lower value, since this is the orange portion of this color bar. But then if you look at the line here, this is around the blue, which is a larger value. Forget about the sign, it is very much larger, that is 200 in magnitude of this current density. That means this is basically a current sheet, and if you try to plot here, the plot is not available for the magnetic field lines, but you can find out that the field lines in these regions and field lines on these regions across this current sheet will have different orientation. It can be very much anti-parallel to each other. Now you know you have anti-parallel field lines, and in between you have a current sheet. Okay, now try to explain the other things. So you can see this arrows are your plasma velocity magnitudes, and plasma velocity magnitude as well as the direction. Okay, so initially you can see everyone is going in the different direction, they are not coming in the current sheet region, right? So what happens is we have part of this current sheet at a certain point, at a certain height, and that perturbation leads to the thinning of the current sheet. That means when you have thinning of the current sheet and you have some formation of plasmoids, then as the plasmoids are forming and in that region, so what is meant by plasmoid? That means they are magnetic islands which have some plasma density associated with it. So as plasmoids moves outward and downward and upward from that particular region, as you can see here, so your total mass in that current sheet region in that particular height will be decreased. So due to the conservation of the mass, what happens, it will accrete, or it will try to have a inflow of the plasma towards that region to conserve the total mass. So that means you have outflow in form of inflow in form of plasmoids, and then it will followed by the inflow of the plasma towards the current sheet. So as you can see, as it goes up and down, your velocity of the plasma changes its directions towards the region, right? And now again another thing is, this is there is nothing like that height have been shown here, but this is with a height in the solar atmosphere. And as you can see that I was talking about the coronal heating problem. So this is majorly a solar coronal reconnection phenomena, but you can see here in the lower region, here you can see that there is something happening in this layer. So what happens is, if you look at here the density plot is not available with me at this point, but still you can find out one thing here is there is some layer which is different from the coronal background density or background parameters, right? So here you can see there is a line, a straight line, one or two straight lines which are defining a different kind of layer, which is basically the transition layer. And you can see the plasmoid which moves up, it goes beyond your numerical boundary, but then you have another plasmoid which is forming like that, and it is not going beyond that layer to the lower layers, rather it goes like this and then it stops and then it bounces back, right? So that means there is some change in the background parameters which is restricting the motion of the plasmoids, and therefore it can give rise to a loop-like structure in a lower solar atmosphere. Okay, so this is your scenario in which you are seeing a numerical experiment where the magnetic reconnection has been happening due to some perturbation in the current sheet, as the current sheet has been perturbed due to some perturbation. In this case, we have perturbed this current sheet by some resistivity, localized resistivity, and as the current sheet is perturbed, therefore it goes to thinning, and as it goes to thinning, that means that there can be the tearing mode instability there, and as tearing mode instability is there, therefore the plasmoids have been formed, and then those plasmoids can go up and down, and as the plasmoids are going up and down, that means the total mass in that particular region in the current sheet going to decrease, and due to the mass conservation, the inflows will start in that particular region. Therefore the reconnection can be happen again and again, right? Because reconnection depends upon your inflow speed, right? So now here the inflow speed will increase since your masses have been carried out up and down by the plasmoids. So as inflow speeds are increasing, therefore your magnetic reconnection rate will increase, and which leads to the fast reconnection rate. Okay, so this is the explanation of this particular scenario. Okay. So if I try to write here the some English there is a current sheet in between numerical box, some perturbation has been given locally in the current sheet, which causes thinning of current sheet, resulting in tearing mode instability and formation of magnetic islands having plasmas well known as plasmoids. Okay, so then plasmoids are going up and down from that particular region, right, which gives rise to the inflow of plasma from surrounding regions, as can be seen from the changes in the direction of the flow, direction of the velocity showing by the arrows. Okay, so this is a brief explanation of this particular scenario. Now, okay, now if we look to the other scenario here, this is one of the work that I have been done during my PhD tenure. So the question is it a reconnection scenario? First of all, let us try to find out what this movie is saying us. So you see here there are some magnetic field lines. These are again the intensity images that are shown in the previous classes. So you can see here there is a magnetic curve structure, and there also here is a magnetic curve structure. Then what happens is, if we go back to the movie's initial stages, you can find out there is some merging in between them, that is the X point that you observe in your classes of right. So then you can have there is some brightening generating, and then it propagates towards the field line, right? So is it a reconnection scenario? Why we are asking is that we are seeing the field lines to come close to each other, so and then afterwards there is some generation of brightening, which means that can be due to some heating, right? So and it can be also due to some more presence of the heated plasma coming from elsewhere, coming from different regions. Now here you can see in this region there is no flow from the outside, so whatever brightening is happening here, it should be due to the heating of the plasma which is already present here, right? So it can be a heating scenario which can be an observational evidence of the magnetic reconnection. So what we do when we do research is you have a intensity image. Now what you can do is you can calculate the differential emission measure in different temperature bands. Let's say you are starting from log T equals to 5.6 to 5.9, which is very low in right, and then you are going to higher temperature of 10 to the power 7 to 7.4. So as you can see that now using those differential emission measure from different temperature bands, you can find out the total emission measure across the entire temperature band available towards us. Okay, then the total emission measure in that particular, let's say in this particular box, can be calculated with time from your data set. So what I found is you have total emission measure calculated from the summation of the differential emission measure in these 6 temperature bands, and it gives me like essentially there is no peak in these regions, and then it peaks or it's rise like this, and then it falls off like this. Okay, so what means by this is the total emission measure which depends upon the density, and density means your intensity. Okay, so this is just inversion technique, not nothing else. So your the density of the hot plasma is increasing as this scenario is going there. So now since there is no flow has been observed from the outside regions coming towards that particular region, so we have only option left that you have plasma already there, but it is getting heated to the higher temperature due to some heating, localized heating, right? So that can be evidence of magnetic reconnection. Also, not only the emission measure, we have calculated the temperature, which is DM weighted temperature, which is not exactly the temperature, but it can be assumed as a proxy of temperature at that particular region. Also, you can find out there is almost an in-phase relation of the DM weighted temperature also in that particular region. So it gives me another evidence that okay, temperature is also increasing, which means heating is there. So from this scenario, from our morphological understanding of magnetic reconnection, like two field lines can be coming close to each other, merge with each other, and then find out there can be some heating depending upon the plasma heating property of magnetic reconnection. We just prove the presence of magnetic connection here in this particular region using the differential emission measure analysis, which is nothing but an inversion technique which invert your intensity images to find out the thermal property of that particular event, okay, in different temperature bands, and using the temporal evolution of the event in different temperature bands, you can find out more thermal information regarding that particular event, which this is what we utilize in this work to prove that there can be a reconnection going on in this particular region, as you can see from this animation. Okay, so I am not going to write many things here, so only what I want to write here is insert answer is yes. Okay. Yes, heating is one of the observational evidence of magnetic reconnection. Okay. Okay, so now if we move to the next question here, is now coming to the space weather events. So what does happen is, you have solar atmosphere, you have solar corona. Now solar corona will have higher temperature, that means it have more kinetic pressure than the gravitational pull, right? So if it has greater gravitational pull, that means if it has outward kinetic pressure which is higher than inward gravitational pull, that can lead to generation of solar wind. Solar wind means it is a flow or it is a flow of the charged particles from the outer atmosphere or outer corona of the sun towards the entire heliosphere. Now our earth is in entire heliosphere, within the heliosphere, so it can have those solar wind charged particles can have some effect on the earth's atmosphere. But now earth will have a magnetic field, magnetosphere, right? So that can leads to stoppage of those charged particles to carry their entire energy or carry their entire energy flux or particle flux to the inner atmosphere of the earth, right? Now this is known as space weather. Now also, as we see in our previous discussions, that there can be solar flares, CMEs. What are like solar flares are depending upon the magnetic reconnection. If there is magnetic reconnection, then some energy will be used to accelerate the charged particles, and those charged particles which are accelerated, what happens are they are going to excited state, and as they try to, so those accelerated charged particles can emit radiation in different energy bands, which is solar flares. Now another thing is the CMEs. Now instead of radiation, this time this is the mass which is going to propagate. So CMEs are basically accompanied with the solar wind. Now solar wind is propagating continuously, but CMEs can happen in some active regions when the sun becomes more active, and CME can come with your solar wind that will have a more larger impact on your Earth's magnetosphere, and it can happen due to the more larger impulse due to the presence of CME. The Earth's magnetosphere can have some magnetic connection also, and which leads to the passage of the charged particles to the inner regions like ionosphere of the Earth's atmosphere, especially from the polar regions, right? Because in the polar regions you can see that the magnetosphere will have some paths which are opened rather than closed. So those charged particles can follow those paths to go to the ionosphere, right? Now depending upon all these informations, if we try to find out what are the correct options here, so auroras caused by geomagnetic storms are generally observed close to the equator, which is not correct, because the auroras basically are observed close to the poles due to the magnetic field structure in that particular regions. Second one is that CMEs are one of the primary drivers of space weather events. So CMEs are one of the primary drivers of space weather events, which is correct. Now, coronagraphs use artificial eclipses in order to observe the solar corona. Absolutely correct. Because solar corona has less density than your on-disk photosphere. So the entire light coming from the photosphere will be very much higher than that light coming from solar corona. So now to observe the solar corona, what you can do is you can use the artificial eclipses so that the higher brightness coming from the disk will get eclipsed, right? So then you can observe it, and coronagraphs exactly do that. Now flares are another name of CMEs, which is not correct, as I was saying that flares are basically radiations, but CMEs are basically the propagation of chunk of plasma instead of only radiations. So those are not same, those are different properties, but they can accompany each other accompany each other often, but it does not mean that every time there is a flare there should be a CME. It can happen that flare is there but CME is not there. So it's not a one-to-one correspondence every time, but it can happen in some cases. So now if we try to find out what are the correct answer, so CMEs are like this, and this B and C are the correct options. What is this? Okay, so a new slide. Now the next one is so you have this one. So if you try to find out what are the connection, so first of all you have sun here, this is your heliosphere, this is your earth, and this one is your so yeah, so this one is your sun, and then this is the solar corona. From there you have passage of solar wind in the entire heliosphere, and you have a magnetosphere around your earth, which have the day side and you have the night side also. So as you move towards this, so it is having some magnetic field which is intergalactic magnetic field. That means it will have some magnetic field associated with it, which is carrying the solar wind. So it has magnetic field, and also your magnetic sphere also have some magnetic field. So in some time what happens, the magnetic field direction in the Earth's magnetosphere is directed towards northward direction. That means from south pole to north pole. Now if your IMF, which is coming from your sun, will have a magnetic field which is directed in the southward direction, then what can happen? Due to the anti-parallel configuration of those two fields, there can be a magnetic reconnection, which leads to the change in the magnetic topology, and also some charged particles can be more energized so that they can move to the ionosphere along these paths. Like now these paths are, this is one path and this is another path. These paths are close to the polar regions of the earth, right? So now as they can move inward from the Earth's magnetosphere towards the ionosphere, they can generate Now these charged particles can interact with the uh, ions in the ionosphere, and they can give some excess energy to those ions, which can lead them to higher excited state. Now anything cannot have a property like they can exist in excited state for long. So as those excited ions are trying to coming back to the less excited states or their ground states, they will emit some radiation, and depending upon the energy between the excited state and the ground state and the ion species, the wavelength of those emission will be different. And what does it mean by the wavelength of emission? That means the color of light which has been emitted by the ion species, right? So this is what we can see if we reside in the polar regions. Okay, so you can see the colorful the scenarios in the night sky due to this interaction of the charged particle coming from the solar wind with the ions in the ionosphere, right? So this is known as the aurora, which is basically visible in the polar regions due to the region that I was explaining right now. Okay, so I am not going to write the answer here. So the next question is like there is a slideshow. So okay, let me write some amount of information here. So also charged particles coming with solar wind can go past Earth's magnetosphere. Magnetosphere to the ionosphere if there is a possibility of magnetic reconnection in day or night side of the magnetosphere. Interaction of this charged particles with the ions in ionosphere leads to excitation of ions. Then as ions are coming back to ground state, they will emit radiation depending upon the energy difference between states. Okay, fine, both. Okay, so this is the answer. Now if we coming back to here in the last question here, so choose the correct options regarding CMEs. So CMEs expand as they propagate, which is correct. Why they expand? Because the pressure, the kinetic, the pressure goes going to decrease, so that means they can expand, right? Then CM is often associated with solar flare, which is correct. We can observe a CME close to the sun as a bright blob because it has lower mass density than the surrounding, which is not correct, right? So brightness has the one-to-one correspondence with the mass density. So CME we can observe like bright blob because it has higher mass density than the surroundings, and then CM is propagated at speeds greater than speed of light, which is not correct. It has speed of, let's say, some kilometer per second or something, so it should not be higher than speed of light. So first two options here are the correct options, so A and B. Okay. Insert just give a new slide here. So that's it for the last interacting session for this course of fluid dynamics for astrophysics. So we started with basic hydrodynamics, then we find out the hydrodynamic shocks, and then we move on to the MHD with the magnetic field along with the basic fluid dynamics. So then we find out that there is ideal MHD regime, and then lastly we went to the discrete MHD, where we discussed some questions on magnetic reconnection, how it can affect the space weather by the presence of solar flares, and CMEs, how the auroras can be formed in the geomagnetic storm, how Earth's magnetosphere can play a role in formation of aurora or the other the geomagnetic storms. Okay, so this much we have covered in our entire discussions. So I think now I am so I have discussed many things in this 12 weeks. So I hope this will be helpful for those people who are interested in this particular field of plasma physics or the solar physics, or even on a larger perspective, the astrophysics, in which fluid dynamics has a huge role to play while you are doing some research work, or even try to understand different phenomena happening in various astrophysical scales. So with this, I will thank all of you again to attend to these lectures, and this is our last session. So thank you very much for your kind attention, and okay, bye bye.